Our plan today is to give an historical overview of the subject. As it was promised, the culmination of the theory will result in the concept of étale cohomology, and the main goal of today's lecture is to explain where did it come from and how it works. The scheme of the history is like André Weil, then Grotendika, who was, there was a very important moment in the theory, one lecture by Sir, and then Grodendijk has finally defined the object we are going to discuss. I'll give some psychological and personal detail of the story. As for the whale part, it seems important to me. I'm not really sure why, that in some of his reminiscences, he said that in 1947 he was in Chicago, as he formulated it, bored, depressed, not knowing what to do, the condition not quite typical for André Weil, since for the whole long period of his activity, he was a very productive mathematician working in diverse domains of mathematics. So he decided just to read something he did not read before. It turned out to be Gauss. So the origins of the theory we are discussing today and have discussed during the semester are rather deep, and they are related to Gaussian arithmetic work. It started with a certain class of equations, namely the Diophantine equations, namely these ones, the equations with two parameters like this. So it happened in 19th century, where the idea to consider the solutions over finite fields was quite original, over FQ was quite original. So the natural problem was to find the integer solutions. So Weyl generalized it a bit and studied the equations in the homogeneous coordinates like I'm writing now. So there was some generalizing root b y to the nth plus c z to the nth, where it was considered in the homogeneous coordinates. So it is a we have a system of complete algebraic curves, giving no name to it. Jump to the 20th century, where the story actually began. I mean, in studying these curves, the number of solutions of these curves, I just write down the number. This question is related to what we have discussed in some initial lectures of the course. It is just a typical functor of points in algebraic geometry. That is one of the approaches to the basic concepts of algebraic geometry. So the theory started with a very down-to-earth question. What is the number of solutions of this equation? The obvious part was the solution, the set of solutions over just residue field, but the deeper question is related to studying the solution over the primary fields, where in some sense R tends to infinity. I'm unable to say something definite about the analogies that were developed by Weyl in that period, but some terribly original intuition was created at that time, and Weyl behaved in quite an unusual theory, in an unusual way, perhaps the unique one in the history of mathematics. I don't know another such example. I mean, there was a dream about a theory that is going to be, I'll formulate it in the most precise way about a theory. In fact, the object to which we have devoted this semester answered is about the realization of this dream in most precise details. So, unlike I'm used to, I'm asking nobody about the questions, I save this screen and start the next one. Save, clear everything. So we discuss, I list the Whale conjectures. So it is Whale 2 years, published 2 years after his feeling bored and depressed. And the actors are as follows. Let X be a variety over F sub Q. Not to work more with the foundational details, let us suppose that it is projective, irreducible, usable, and smooth. So the question we address, as in the previous whiteboard, is the number, in fact, is the behavior of the functor of points over the extensions of the ground field. Let us fix, let's use the same letter here. And so we are working with one of the most observable quantity in the world, just counting things. It was rather difficult in 1949 and extremely easy now using the available software. So what we are discussing now is belongs to the experimental mathematics. Basically, we are trying to explain the phenomena that are very easily observed and belong to the world of natural numbers. I just mean countings. So the way to count them was very well known in that time, and the official name is the Hasse-Weil zeta. Hasse-Weil zeta. It is a special kind of generating functions of these quantity. Now the standard notation, for which I perhaps use some other color, or maybe the same red color, is it is Z. Well, it is not a letter, a Latin letter that we have deep reasons to hate now in the spring of 2022. But it is really the large Greek letter. So by definition, it is a peculiar generating function of x being the sum from R running from 1 to infinity of the number of points of just the quantities we are interested in, x of f of the field of the cardinality q to the rth t to r, and r in the denominator. Well, this object, this seemingly transcendental power series that could carry infinite number of information, is in fact the rational function, turns out to be a rational function. It is by no means trivial fact, but anyhow, what is important now, I want to emphasize now, is that the whole countable number of quantities is described by a finite amount of information. Now we return to the precise conjectures, numbered and called. So while conjecture 1 called rationality, write it here. There is a much more precise information than just to claim that this function is rational. It is being observed and generally supposed that the numerators and denominators of these functions factorize in quite a special way with the odd indexed polynomials in the numerator and so this is like this, odd functions in the numerator. Now perhaps some comments about this twice d, especially since the even labeled polynomials in the denominator run from p0 to p sub 2d of x t. All these polynomials turn out to have an enigmatic but somewhat clear geometric meaning. In the case where x, our main variety x, is a reduction of a variety defined over integers, it can be considered over complex numbers. I'll say more about that soon. Now I'm just explaining the index in the number 2D. And then the related geometry can be calculated in terms of topology of that complex variety that is 2D dimensional, considered as a real variety. So what is really supposed for the time being, just so this kind of factorization where phi A belong to just Q bar of T. In this form, the statement is almost void, but soon in the other conjectures, we will give an interpretation of the degrees of all these 2D plus 1 polynomials. Now the next one is called integrality. Much stronger statements can be integrality can be made. That is, first of all, the extreme polynomials are written explicitly. 1 minus t, and the last one you can prepare to understand them in the topological terms. Of course, it would be much better if we had more time to discuss these axioms with examples, both available to Gauss and Weyl, and to other peoples. As for the other polynomials, then the p sub k's of x t is the product by I. We'll soon know what is the number of I. 1 minus a sub k I t. So it's factored in the linear factors, and all these anti-roots of the polynomial of our polynomials are algebraic integers. Unfortunately, there is no universally accepted notation for it, so I use this one as the integers of the field Q bar. So this is just 2 over 5 axiom. W3. Sorry, so that is called the functional equation. And I interrupt myself to say something maybe very well known, that various zeta functions are associated to different kinds of schemes of the object of algebraic geometry. And among them, there is a Riemann zeta function associated just to the spectrum of Z, of the ring of integers. And the equation we are going to write down now is a direct analog of the functional equation of Riemann zeta function, because of which it can be treated as a meromorphic function in the whole complex plane. The analogy is deep, though the whole bunch of axioms are proved in this special case we are discussing in the algebraic geometry over finite fields, and still open. The next one is still open in this beginning of the third millennium. It is one of them. The next one will be one of the 7 open problems for the coming 1,000 years. So the functional equation looks as follows: z of x when we make the change of the argument. Recall that d is the dimension of our manifold, and then there is a plus minus that we don't discuss now. It is a rather delicate object. Now q goes to the following nice number. In fact, it is the Euler characteristic of a manifold. This is by no means obvious how to define the Euler characteristic in the finite over the finite field, where there are no, at least initially, there are no Betty numbers to take the alternating sums. So we introduce the diagonal of any object as a subset of its square, and then use the definition of Euler characteristics of a compact variety as the self-intersection of the diagonal, and then return. It is just a coefficient for the functional equation. Now, the fourth one is the most important and is covered exactly by my previous comments. It was the most difficult one in proving, and still open in the analog of this object related to the spectrum, the analog of this object related to the simplest variety over integers, that is the spectrum of integers itself. So the formulation is quite straightforward. it tells something about the absolute value of the roots. So here I use the notation for gamma being the absolute Galois group. And it turns out that all the roots of this pi I lie on the concentric circles centered at 0, and their orbits ki are precisely q 2 half k. So the picture is like, perhaps I can try to draw it. So the roots lie in the no, it doesn't help. Sorry. I mean the available tools. So the roots of various polynomials participating in the zeta function lie on the certain circles, and the radii of these circles depend on the, so to say, dimensions. When we understand better what it is about, depend on the geometry of the cycles of the corresponding dimension, while their number, as for their number, this is the last conjecture. Sorry, I didn't say that it is called Riemann. Oh, this is, well, after certain reformulations, let me just remind you that when we work in just in the complex domain with the S here and 0 here, 1 here, and here is the critical strip, and the Riemann conjecture, still open, tells us that the non-trivial 0, unlike the ones that are trivial and lie in the odd negative integers, all lie in the real line, having the real part a half, just lie in the X of symmetry of the critical strip. So after certain reformulation, this conjecture is the analog to the Weil conjecture number 4. And finally, the fifth one is the only one that is somehow related, more or less explicitly related to the matter of our course. So now suppose that our X is the reduction. That's written down in the modern way, well, modern after Grothendieck, that it is a reduction, a result of the base change over spectrum of Z to the spectrum, the funny spectrum of 1-point spectrum of a field. So this is the basic object. So it means that X, well, let's write it down explicitly. Suppose X hat is defined over Z. Then in this case, and by the way, only in this case, we are able to understand completely what do the powers, the degrees of our polynomials mean geometrically, or in other words, what is the number of the roots or entire roots. They are not roots, but their inverses are the roots of our polynomials. So what is their numbers on the corresponding circles? And they are the last conjecture says that these, in this case, the degrees of our P sub k, well, I don't write in T because this is the only variable about which it depends, are just the beta numbers. Let's write it down as the dimensions, or rather okay, write it like this, the dimensions over Q of the cohomology of this variety over integers with coefficients in Q. So this is the most strange relation between the arithmetic of the reductions of varieties defined over integers and the topology of their complexification. Okay, if I knew whom I am speaking with, I would ask whether there are any questions, but perhaps for the time being the cardinality of the set of listeners is empty. So I have no place here to relate these conjectures. Finally proved this one by Deligne much later, after several decades, and having developed a very deep and important machine, not only for this conjecture, but for the whole mathematics. This miracle cries out for some explanation. I mean, perhaps it cried out even for Whale. And well, the modern, the true dream that was mentioned before is about, was about certain cohomology theory of the varieties over finite fields. By the way, in less than a decade, some perfect cohomology theory was created by Serre with coefficients, the theory of cohomology with coefficients in arbitrary sheaves that worked for any varieties over any schemes, but it was not what Weil dreamed about, because the corresponding Serre cohomology, Serre sheaf cohomology, were defined over the fields of the positive characteristics in this case, while what I'll write down now, perhaps having erased the question mark, but keeping the red color to formulate the dream. So the dream was that these P sub k would have quite a definite cohomological sense. They were and turned out to be the characteristic polynomials, cohomological polynomials. More precisely, the determinants of 1 minus Frobenius, the automorphism defined over the, well, same manifold defined over the algebraic closure of the finite field. Well, let me write it down explicitly. So this Frobenius, let's put a star here. It acts on the unknown, not yet defined cohomologies of what? Of x bar with the coefficients of QL, Q sub L, L-adic coefficients, T times D. So this is kind of anti-characteristic polynomials, where these cohomologies just had to be invented, while x bar is just x raised to the algebraic closure. That is again over spectrum Fk with spectrum Fq bar. So the task was just to invent these cohomologies. As you see, this circle of ideas belongs to the classical arithmetic. It has nothing to do with the complicated abstract foundations of the algebraic geometry started by Grothendika. However, there were no other ways to explain this arithmetic phenomenon, but the ones that actually happened in the further development. So this is the part related to whale in the whole history, and this is the half of our lecture, and we'll have a break for several minutes. Okay, now we continue. Save this one and clear, and turn to search to the next part, that is Jean-Pierre Serre's lecture. That is by some historians, it is called the birthday of Grothendieck topologies. And it took place, the birthday has a right to be marked precisely, so it was the 21st of April in 1959. As we see, just 10 years after the publication of Wales' dreams, and superficially in the discussion of the problems that had nothing to do with number of points of varieties over a finite field. However, as some historian that I'm not going to fix now formulated that this was the day, perhaps I mark it. It was the day when our notion of neighborhood, of course, neighborhood of a point somewhere, neighborhood, would change forever. Serre's talk was called was about algebraic fiber bonds or bundles. Espace fibré algébrique. And according to the general direction of Serre's activity there, the best mathematicians of France worked over the foundations of algebraic geometry, trying to make them more geometric, and the analogies with the other geometric theories, first of all, with the theories of smooth varieties, real smooth varieties, to make them more explicit. And the precise problem that Serre met was that for a very good action of a group on a variety, Serre, the group can be supposed reductive, that is the product of a semi-simple and its center, and the variety could be supposed as smooth projective. The morphism, the factor and the morphism can be in general defined, so they are definable. However, they rarely, this arrow, but this arrow rarely has the property that we find in the smooth category, has the local product, co-product property. The one that can be symbolically drawn and lie in the center of the theory of vibration of different kinds, and the construction of which Serre took quite an active part. And this idea of well, the orbits being the principal homogeneous space and spaces, and the pieces of the vibrations being locally, behaving locally like products, did not had no algebra geometric analog, and the explanation was quite simple, that Zariski topology had a poor enough open sets, not enough opens. So from a wider point of view, the problem is similar to the construction of the appropriate cohomological theory, because if we try to imitate any cohomology theories from the classical topological approach, for example, trying to construct the Czech cohomology, then we find out that having an irreducible variety, we have the homotopical trivial nerves of any coverings. If I remind what a nerve it is something like that. And the Zariski opens are too big, all of them intersect, and therefore the nerves that are the basis of Czech cohomology theory are all standard simplices. And there was the question how to expand, how to enrich the amount of open sets. The classical direction was to replace the Zariski topology by the complex one, and then we have lots of small open sets, and construct any cohomology theory we like. But in the abstract setting, the direction was different, and Serre himself used the base change. Serre, let me mark that it was Serre himself used the and Étale, of course, and Étale base change y over x, on which the group acts, and arrived at the classification problem. So she arrived at the usual group that classifies the fiber bundles, that is H1, H upper 1 of X. J defined somehow in a rather technical way in terms of this Y with the subsequent proof of an independence of the base change. So this is the first Étale cohomology that appeared in mathematics, and that's why this day can be really called the beginning of the whole theory. And Grothendieck was among the listeners of this talk. Grothendieck, who felt immediately that these are the true cohomology to prove Weyl conjectures. So it was his idea, as I have told, it was after 10 years after the conjectures were formulated. But well, the advanced mathematicians remembered about it. And of course, this was a flash of genius whom Grothendieck was. And maybe the history would be quite different if, for example, Grothendieck paid no attention to it. By the way, as historians say, the Sir was quite skeptical about it, but Grothendieck was used to have his own ways. So this birth of this kind of topology, of cohomology, was almost accidental, seemed to be almost accidental, but now we'll save it and turn to the next whiteboard, considering the next part. So it is now Grothendieck considered it quite seriously, and then several strongest mathematicians shared his view. The most active of them, Michael Artin, and Verdier, but I'll speak about Artin because his lecture notes, now quite available in the internet, was the first official source about Grothendieck topology, developing Grothendieck topologies, the theory of now we finally come to the heart of this course, and I have to admit that during these lectures I have never given the precise definition of Grothendieck topology. I'll do it now, following Artin, but well, with some important comments about these definitions that I'm going to write down, being maybe not the final ones. And I'll remember what we have discussed. So when we discussed classical topologies, I was trying, perhaps I write down topology as a branch of mathematics. I was trying to emphasize that the concepts were of the classical topology were very close to leaving the set theoretical mathematics. In other words, let me remind those who visited that lectures that for topological space an object of the usual category of topological space, we have defined two categories. Categories of open sets and of coverings of X. Open sets was small, and that is the most important set theoretical property of it, that is not shared by the Grothendieck topology. Put a bit another way, so the morphisms in this category of open sets of topological space were just open inclusions, and maybe I should emphasize that it has the final object the X itself. And when we think about various operations with topological spaces, we can just ask ourselves, do we really need these final object? And it turns out that in many constructions, the answer is no. And the cohomology theory, to a large extent, can be constructed without it. And there was another issue about sets and categories. So this was not small at all, because we have defined it as the category of pairs I and U, where U was sorry, I was an arbitrary set, and U was just choosing of an open set of X. And there were some reasons to consider among the indexes of coverings arbitrary sets. Therefore, the category was by no means small. Now I should admit some methodical mistake I've made. Then it would be better at that preliminary stage, better to consider a bunch of such categories, consider well, I'm not going to use the set theoretical arrows now, but all these pairs opens U sub U and coverings sub U for all the U that were open sets, but I'm writing them as denoting them as the objects of a category. After taking this point of view, we can arrive at the official definition of the Grothendieck topology in a very straightforward manner. You can answer the question what a Grothendieck topology is using any of the available sources in the modern world, Googling it and so on, and you come to a rather difficult abstract concepts. It is just because of this delicate question: are we working with sets or categories? As I claimed it in the lectures, one of the most important steps, now I would call it just a very important step, is stepping beyond the counter paradise, beyond the set theoretical mathematics. But Grothendieck was not interested in these details at all. If you take the official definitions, you run into rather complicated definitions of sites and sieves and some others. I'm saying about it now because as soon as we turn to the original lectures by Mike Arton, we'll find out that the definitions are much simpler if we just ignore the set theoretical issues. This is what I'm going to do now. So now suppose that we are not worried by the possibilities of mixing all the sets of indexes and things like that. Then briefly, the definition of Grothendieck topology will become almost as short as the definition of the classical topological space. So there are again two categories again. Oh no, sorry, here called Artin says that he considers one category and one set, but we have agreed to ignore the difference. So we answer the question, what is a topology T? So if you find Artin's notes of 1962, you will notice that it was in the pre-computer era and pre-tech era. So there were no fonts that we are using in our course to distinguish the objects of a different level of abstraction. So I'll just follow his notation. Here is a topology T. That in the modern, from the modern point of view, is something like category or two category, but we have agreed to ignore it. So there is a pair with the self-clarifying notations. Category T is, of course, the category of opens, and coverings. T is the category of coverings. And there are exactly three axioms. Again, like with Veil, with its names, sorry, I have given a name to, yes, to all the three. So the first one, let's call it, maybe the names are not official. I write it in different color. One element covering. So in the brief notation, so the axiom is whenever is that this kind, that when we have an isomorphism of objects, of course, you and others are the objects of the category T. Sorry, I should give some intuition to it. When we want to relate the objects of Grothendieck topology with the classical topology, we think this way. So we consider, we mean some abstract true open subsets. And for example, in algebraic geometry, we consider there the isomorphisms or the non-ramified coverings, something like that, but still call them U and so on. So when the isomorphisms imply the isomorphism are the trivial coverings. So belong to cover D. Now the second one that I call distributivity, and we'll comment in a while about it. Distributivity tells us that whenever we have a covering U sub I of U, and every U sub I is covered by V sub ij, then the covering V I sub ij also belong to coverings. In a while, I'll explain why this is the distributivity. Of course, this is these sets are the compositions, and I omit, among other things, all the quantifiers, meaning that all these i's and g's are arbitrary. Now, why is it called distributivity? We have not much time, so please think about it yourself. Well, the blue is the color of questions, and I suggest you to think about the classical analogs. And finally, there is the third component. Well, the category, of course, had to be assumed to have fiber products. And then the last one, that is what the axiom of base changes. Is plural, perhaps. No, people don't use plural here. So now, whenever u sub I to u is a covering, and v to u is a covering, then it implies that taking the fiber products u sub I over u with v to v again belongs, again is a covering, belongs to sorry, no error here, no arrow here. It is just an analog of the open set again, just belongs here. So these are three short axioms. The number 3 is strangely rather typical for being the cardinality of the set of axioms. We can remember that the groups are defined in 3 axioms and classical topological spaces as well. And these one are as short as the just mentioned axiom systems. As, sorry for repeating it again, the only problem is here that if we stick to the modern and rather rigorous attitude to the set theoretical foundations of what we are doing, then we should add much more, add more words about it, taking care of well, distinguishing between sets and categories. However, there are two ways we can consider small Grothendieck categories, and perhaps it would be sufficient in order to satisfy the whale's dream. But all these restrictions, in fact, would be quite unnatural. And I think we should trust the Grothendieck's intuition, who just preferred to ignore it. He didn't ignore it completely because he was a rigorous person and lectured a lot. So he invented such things as Grothendieck University. But I think that maybe this concept will not survive in the future. And I think it is possible that in the future, people will be not so afraid of the antinomic problems as we are today. And just maybe formulate some rules that will allow them, the mathematicians of the future, not to be so touchy about well, possibilities of a set of all sets and things like that. The historical analogy could be if we think about the mathematicians several centuries ago, they were quite suspicious about negative numbers or imaginary numbers. And there was a feeling that there are true numbers, the natural ones are the cardinalities of something we can hold on, and so on. And well, the name of imaginary number is self-explaining. So it may happen that the mathematics develop in such a way that this set of axioms you see on the right of this whiteboard is going to be quite fundamental as we now understand the axioms of the groups. And by the way, we can recall that in Galois' time, the concept of group was by no means not so clear because people were used to the concepts, to more classical concepts. Anyhow, it is what I was speaking about for several minutes is nothing but a fantasy about the future of the subject of this course. And now, during the last minutes of the last lecture, I just save this one and clear everything and just claim that under the taken axiom in Grothendieck topology, the whale cohomology can be defined in quite a natural way. Quite a natural way. the constructible sheaves below sheaves over Grothendieck topology, which are defined in quite a natural way. So for any covering, well, for a scheme, base scheme X, and any sub scheme Y or sub topology, we have that the constructibility means that for any covering U sub I of Y the sheaves of abelian groups. So it would mean that I upper star Y sheaves F are just finite and locally constant. And then constant. And then the desired cohomology, after we have all these concepts are constructed rather straightforwardly in a Czech manner, analogs of Czech cohomology that I have to assume known. Czech cohomology can be defined this way. So H, say, the whole well, I'll write it like this. The cohomology like this are defined quite straightforwardly with the locally constant, with the constructible sheaf, and then some limits over F is defined and becomes the cohomology, the Untitled cohomology of X with the L-adic coefficients. For example, for a curve that satisfies the Weyl's original intention, for a curve X, we construct the cohomology of, we are interested in the first cohomology, and we define them in the coefficients of N Z. This is the constructible sheaf. Then can be given some interpretation in terms of Picard of the curve X. And then we just take the limit by n and get the true cohomology with the L-adic coefficient, or rather with integer L-adic coefficient. L is just a prime. Well, which are the characteristics of the base field. Q is the power of some other prime. So these cohomology work, but they are very particular case of quite a general theory, and there is a very detailed handbook by МИАН where you can find all the details. So the whole story with which I close this course is about some down-to-earth questions of just counting solution of equations, questions perhaps as ancient as mathematics itself, that gave one of the most powerful extension of such an advanced discipline as algebraic geometry. And now they coexist in some harmony. Maybe that has not reached its pedagogical excellence, because, for example, you'll see that the book by МИАН is very difficult to read, but you can be sure that you find all the details here. Okay, so we close now, and best wishes to those who possibly hear what I've said today, and somehow some people are interested in having the grade for the exam about this course, then write me please, and we'll make some decision about that. Bye, and best wishes in these terrible times.